So in November 21, we were finishing off on question 4. Well, we're almost done. These are reaction questions in organic chemistry. And so we had a nice summary here, a nice summary page of all the possible things that we might need to know on organic chemistry reactions, addition, elimination, and substitution. And so let's have a look. We're going to maybe refer back to this page on a regular basis as we finish off on this question 4 from 2021 paper 2. And this question 4 points in us says, okay, 1,2-dibromopropane, okay, can be prepared from but2ene by a 3-step process as shown in the flow diagram below. This was an interesting question for me. This is not often seen, where they show multiple steps of unknown waves. So but2ene goes to compound A, goes to compound B, and then dibromopropane. This struck me quite interesting. I would like to hear from you, Emilie. How do we go from something like but2ene to something like a bromopropane? Do you have any idea? Like, initially I was thinking elimination and addition, but I think there's a bigger issue here. Can you spot what might be a much greater issue for us than just elimination and addition? I think what sort of stood out was the fact that this has got 4 carbons in its chain, and this only has 3 carbons in its chain. So somewhere we had to break this carbon up. What was that process called? Do you remember the name of that process called that breaks up longer chains into shorter chains?
Yes, sir.
It's cracking, right? So
That's correct.
it's cracking. Yeah, somewhere we're gonna need cracking here. And I don't know if you remember, but cracking, does that take place with alkenes, ines, or anes? Now, it's per definition, it's mainly works with alkanes. And so if we have a look here at elimination reactions, really the one that we work with when we're looking at cracking or elimination reactions in cracking, we always go from longer alkane chains. And then from the alkane chains, we find shorter alkanes plus an alkene. Okay, so it is important for us just to note that we will need to, before we do this cracking, we will need to go to an alkane first. And I think that's the important step here, is that there's a 2-step process, a step 1 and a step 2, to go to a final step where we might be adding. Okay, and so this, I think this looks like addition. But what's important for us is somewhere along the lines here, I have cracking, okay? But our cracking doesn't happen with butenes. And so how do we go from enes to anes? How do we go from an alkene to an alkane? Now this is just the addition of hydrogens, right? So going from an ene to an alkane, this I am almost 100% sure is an alkane. And so hydrogenation, right? So this is most likely hydrogenation. And you can see just by interpreting the question, we can maybe answer, we've prepared ourselves for what is to come. Compound A to compound B, an alkane to something again that we can add to, right? Now, again, adding to, going from an alkane to something that we can add to that is a propane. Oh my goodness. So we need to go from an alkane that has 4 carbons in its chain to something that only has 3 carbons. And so this is going to be the cracking. That's the cracking step. So let's have a look. Right, now we have a look at the question. We say, well, 4.2.1, using condensed structural formulae, write down a balanced equation for step 1. Again, we've already, see, by looking at this, by understanding, by interpreting this equation, this situation first, we've sort of got the answer already. So condensed structural formula, remember I told you we do not allow any bonds in condensed structural formula. Okay, in condensed. And so we're going to make sure that we follow those rules. They become a lot stricter on this these days. For step 1, that is but2-ene, and so that we have carbon and a double bond, carbon with a double bond to a carbon. So there's 4 carbons, but how many carbons do we have bonded to each one? Need to figure out. You can draw the structural formula if you like this, and then make sure you have the hydrogens. So it's 3 hydrogens on the first, 1 hydrogen on the second, 1 hydrogen on the third, and 3 hydrogens on the last. Okay, on the other end, write down the balanced equation. So that's the for butene, and then I'm adding, or what do I need? What is need for hydrogenation, or do we need any what do we call it, reaction conditions for hydrogenation? Do you remember what the reaction conditions were for hydrogenation?
No, sir, I don't recall any conditions. I only recall that we don't use water.
There was, yeah, definitely not water in this case, because otherwise we will be creating an alcohol, right? So, but definitely an excess of hydrogen. There was one extra addition, and it was a catalyst. It's either platinum or nickel, I think. We can have a look here quickly. Let's go to our summary pages, and this is going to be study work. Platinum, nickel, or palladium, PD. I like platinum. It's a very common catalyst whenever we're working with hydrogen things, even with galvanic cells. The hydrogen half cell also works with a platinum catalyst, which is again a nice thing. So whenever it's a good thing, a nice one to remember, that sometimes if my mind rings to tell me that I need a catalyst and I'm working with hydrogen, platinum is a safe bet. Okay. So now we're looking at compound A, alkene. We need the products. We're going to have that this hydrogen is forming CH3, CH2, CH2, CH3, and this is an alkane. This is butane, right? And this is going to be our condensed structure formula for the reaction condition. A good indicator that we needed a platinum catalyst as well was that this was a 4-mark question. 1 for each reactant, 1 for the product, and then 1 for the condition, right? So sometimes, again, looking at the reaction, looking at the marking allocation can help us. So 4.2.2, write down the type of reaction in step 2. Look what we've done. We've interpreted this is cracking, or I would suggest rather going elimination and then mentioning cracking. We know the very specific type of elimination that took place, but elimination is the type of reaction. So it's elimination is the more broad reaction name, but cracking is the more specific one. Okay, so 2.2.3. It's interesting. In a sense, I would, as I mentioned, I would suggest putting cracking second, because say we aren't 100% sure about cracking, but we are 100% sure about elimination. Often the memo allows elimination as an answer over cracking. More often than not, it actually allows it. And so the general rule of thumb is, even if cracking was wrong, they would always mark your first answer. And so even if cracking was wrong, you'd still get the answer. You still get your mark by answering it like this. Whereas if you said cracking first and then elimination, even though elimination was right, cracking was wrong, and so they have to mark your first answer. Right, so I wouldn't say it's calling a cheat in the system, but it is a safe space, a safe way to answer. Now, next, write down the IUPAC name of compound B, and that's where we need to understand what cracking is happening now. What type of cracking is taking place? We've got an alkane of 4 chains like this that is breaking up into something that has a propane. So it's breaking up into something that has 3 chains and something that has 1 carbon in it. Okay. And just a reminder of what cracking, the products of cracking are. generally, for the most part, the products of cracking are an alkane and an alkene. Okay, both of shorter chain length. Now, this one carbon cannot be an alkene. Okay, so
I think so.
again,
It's a it's an it's a propene.
it's a
The
propene.
product will
Yeah, and it would be double bond on the E. It's so like this. Okay, and so
on the first cup.
yeah. Would it be wrong of me to put the double bond there?
No, sir.
Yeah, it's the same, right? Now what, I just need to number it from the opposite side. Okay.
Yes.
So it's either way, it's fine. But write down the IUPAC name, and so the IUPAC name would be propene, you said, right? Oh, let me try black. And that is 100% correct. It is propene. You can go prop 1-ene, you can go 1-propene. All of these are fine. We don't necessarily need to indicate the position because there is only one possible position in naming. Okay, so propene on its own should be enough. Now let's have a look at 4.2.4. Using the condensed structural formula, write down a balanced equation of step 3. And this is where we go again. We need to make sure that we know what we're starting with. And so we can draw ourselves a little propene if we like. We've got 2 hydrogens. We've got 1 hydrogen and then 3 hydrogens on that. Okay, and so we can go CH2, CH, CH3. All right. So again, I would not suggest pointing out any double bonds, although technically we could. It is something of the past to show a double bond there. As I mentioned, we're going to, for condensed structural formulas, now not anymore allow any bonds to be shown. Okay, you might see as you go through old exam papers on your own that they still and sometimes show that double bond over there. My suggestion to you is do not show it anymore. They've become very strict. So let's write down the balanced equation. This is our propene. And then what are we adding to make dibromopropane?
Sorry, sir. Can you repeat?
Yeah, so we got propene here. And then what do we need to create 1,2-dibromopropane? What are the other reactants?
We need 2 bromos.
Yeah, 2 bromos, and then become in the form of bromine gas, okay, which is quite nice. This creates our 1,2-dimopropane, okay, and are there any other byproducts with just pure addition like this?
Yes, so the product will be CH2, CH, CH will be CH2, CH, then Br. The bromo will be connected to the CH.
Yeah. So I would maybe with how I've drawn it. Okay, so you're right. You can say that CH 2, but remember, if we're going to be drawing it out real quick, I'm just going to draw the condensed structural formula just to show it. We've got the 2 hydrogens. We had the double bond to the carbon with hydrogen there. I'm just going to ask that you bear with me for a moment, just to make sure that we get the naming structure perfectly correct. A bromine gas, they will come here. This double bond will break open and we will form this right there. Okay, so the double bond breaks open and forms the bonds to the bromines here. I think what's just important here is, was it the carbon that had 3 that it was not the carbon that had the 3 hydrogens that got a bromine. It was the carbon that had 2 hydrogens that got the bromine. And so if I'm going to name it now here, the CH2 actually gets next to it a bromine. it's that carbon that has the two hydrogens that has the bromine. And then I go, okay, CH, Br, and then CH3. Okay. This is one way of naming the molecule. There is another way of naming it. For example, if you name this molecule, if you'd have the CH2 on the right-hand side. So for example, I'm going to do this next part in green. If I had CH3, CH, CH2. So it's exactly the same molecule. Can you see that?
Yes, sir.
Yeah. And so if this would take place, we'd have CH3, CH and bromine, and then CH2.
True.
Yeah. Both of these are correct, but it is important in how we've drawn our starting products. If I start with this black version right here, CH2, CH, CH3, then I'd highly encourage you to keep that order the same. The CH2 and the CH and the CH3 with the bromine attached to this carbon and this bromine attached to this carbon. Okay? It's just consistency rather than anything else. Okay. So sometimes you won't see more than one answer in memos. They often don't. But in memo discussions after the test has been written, they always make this addition. They always make the allowance for both. Okay. So just please make sure that you take note of that. Nice. Okay. So, and I mean, that's it for reactions. Sometimes just by taking time, like we did in this previous one, just taking the time to understand, to interpret the question, prepares us more than well enough for what the questions are to come. Again, we just took us some time to prepare ourselves understanding the question, and we were overly prepared for what was to come. All right. And as we move past the organic chemistry, just a reminder, do not show any bonds on condensed structural formula, not even double bonds or triple bonds. In old exam papers, they will say they allow showing the double bonds and triple bonds, but for this exam coming up, they will not be there. We've explicitly been told this by the department. Okay, so let's continue on to question 5. It's question 5 in the November papers. In paper 2 are almost always reaction rate. That's pretty standard. And we need to just remind ourselves, what are the things that affect reaction rate? Okay, a big one is always temperature. Temperature quite affects reaction rate quite heavily. All right. Excuse me, just taking a sip of water. So first off, 5.1, define the term rate of reaction or reaction rate. And okay, marking guidelines tells us, well, that will be, it's essentially, it's just a formula. Change in concentration per unit time. Those are the most important parts. And so let's write it out. We've got the reaction rate is change in concentration of products / reactants per unit time. And the important parts there are change in concentration per unit time. Right, so let's just underline those again. Change in concentration per unit time. If you're missing out on one of them, you might not even get any marks. This is the type of question that they say all or nothing. Okay, 2 or 0 if you're missing out on even one of those 2 underlined sections. Okay. So 1.5.2, give a reason why the gradient of this graph. Oh, hold on. Let's just first understand what the question is asking. A reaction of 15 grams of impure sample of calcium carbonate, CaCO3, with excess hydrochloric acid. That's a base and an acid. Of concentration 1 mole per cubic decimeter is used to investigate the rate of reaction. The balanced equation of the reaction is given here. It does seem balanced as well. So if I briefly have a look at it, the volume of CO2 produced is measured at regular intervals. A sketch representing the total volume of CO2. Okay, so the total volume of one of the products is being measured, and it's sketched here over time. So now they give a reason why the gradient of the graph decreases. So here between T2 and T3, gradient actually becomes flatter. Now, I mean, we can write the whole paragraph here, but for for one question, for 1 mark. Please don't give a whole paragraph. It is entirely unnecessary. They're building on the previous question. Often with these questions in science, both physics and chemistry, they like to build on the previous one. And so if they're talking about reaction rate in the previous one, they like to talk about reaction rate now. And so give the reason why the gradients of the graph, change in volume or change of some substance per time, that is reaction rate. So the reaction rate is decreasing. The reaction rate decreases. That's why the gradient decreases. Okay, 5.3. That's going to be 5.3.1, 5.3.2. Changes in the graph between T1 and T2 are due to temperature changes. Look at that, temperature changes I mentioned earlier within the reaction mixture. Do you remember anything how temperature affects reaction rate?
Yes, I do.
What does an increase in temperature do to the reaction rate? It increases the reaction rate, right? So if I've got a reaction rate between T1 and T2, this gradient is actually increasing. Okay, and so if the gradient is increasing, that means that the reaction rate is increasing. That means this is an exothermic. Is it exothermic or endothermic?
Exothermic.
Is it
Exothermic.
Exothermic reaction. That's right. All right, and 5.3.2, explain the answer by referring to the graph. And I sort of mentioned a lot of these points already now, but just again, to make sure that we're getting all 3 marks, we're going to make 3 statements, right? So in these explanations, very similar to the intermolecular force questions, we're also going to just make sure we make 3 lines of statements. We start off with the obvious. The gradient is increasing. Okay, gradient is increasing. Second line is, well, what does that mean for us? That means that the reaction rate is increasing. Okay, and what is
That line speak about the temperature that increases.
That's what we're going for, right? We need to explain this, and so we need to talk about that. Lastly, the temperature is increasing. Yeah, 100%, 100% increasing. Very good, very good. Okay, so the temperature is increasing. 3 statements,
Sorry, sir.
3 marks. Yeah, go for it.
In these points, is it appropriate to speak about the average kinetic energy? Because it increases.
Yeah, if I would say, if you want to mention that the average kinetic energy is increasing, that's a valid point. It would take the place. It would be in this last statement. It would fall along the lines of temperature increasing, because an average kinetic energy increasing, average kinetic energy of particles is how we measure temperature. So it would fall in line with this. Yeah, and so 100%, I would say, because it is the definition, that is a very acute, a very good statement from you, is it would really just be a different way of saying temperature increases. Okay.
Putting the
average.
Okay, so
yeah, average kinetic energy increases, because this is by definition what temperature is. This would be exactly the same as temperature is increasing, right? Cool. So let's continue on. Let's go 5.4. This is a 5-mark question. Let's have a look. The percentage purity of the sample. Are they giving us a percentage purity? That's a wonderful breath of fresh air. Calculate the value of X on the graph. Okay, assuming that the gas collected is collected at 25 degrees Celsius, take the molar gas volume at 25 degrees is 24,000 cubic centimeters. Okay, let's have a look here. This value of X, I've got the volume, that's the volume of gas that we're trying to calculate. And this is, look at this reaction rate. The reaction rate is slowed all the way down. This is when the reaction has gone to completion. Okay, so this is when all the products are used up and the reactants have been made. Okay, so we know how much products we have because they tell us the percentage purity of the sample. Okay, so we know how much, or at least we can calculate how much calcium carbonate we started with. And if we know how much calcium carbonate we started with, that is, if the gradient is flat, that means the reaction has gone to completion. And so that really does mean all the reactants have formed products. And so I need to know, this is, I think, standard stoichiometry. Okay, so let's have a look first. They started with 15 grams of impure calcium carbonate, but they tell us 82.5. And so the mass of, and I'm going to write this out, the mass of pure calcium carbonate. Now, I'd suggest you do the same, and when you do stoichiometry questions, write down just short descriptions of what you do. It not only helps the marker that is very tired, I can promise you, but it also helps you just, keep your mind, keep your head on your shoulders in what you're doing. Mass of the pure calcium carbonate is 82.5% of the original mass. And so 82.5% of 15. And calculator's out. Well, then where's my calculator? Here I have it somewhere.
12,375, sir.
Say again, is it?
12,375.
12,375. Beautiful. Okay. And that is grams, right? That is, we're calculating the amount of grams. I'll find, right, here it is. Okay, cool. So now we've got the mass. Now we can go to moles because the reaction rate is in molar ratio. So we have moles of calcium carbonate in ratio to moles of the CO2 gas. This is a 1-to-1 ratio. But hold on, we don't have moles here. So let's first calculate the amount of moles of calcium carbonate. Oops. Moles is mass over molecular mass. We have 12,375. And calcium carbonate, I think that's 100, isn't it? You sort of get used to these values. I don't have my periodic table with me. I'd call me a bad teacher, science teacher, if I don't have a periodic table as my background somewhere. All right, but let's have a look. I think it is 100. Did you calculate to be 100?
Yes, sir.
Okay, awesome. Thanks. All right, so, and then calculators out, we can say that this is going to be equal to 0,124. All right, of course, it's divided by 100. 12375, but let's round up to 3 decimals. I would argue maybe 4 decimals, but let's just go with 3 for now. This is the amount of moles, and now this is, for that same reason, it's the same amount of moles of carbon dioxide gas. Now, generally, they tell us we've got the molar gas volume formula, but now they've given us the molar gas volume at this very specific temperature. And so, excuse me, we can calculate the volume that will be equal to moles multiplied by the molar gas volume. And so this is 0,123 multiplied by, how do we measure volume? Generally, it's SI units as our cubic decimeters, right? Right, and so for that reason, I would much likely, I prefer actually to do this conversion over to cubic decimeters. Okay, from cubic centimeters to cubic decimeters, that would be divide by 1,000. Okay.
Yes, sir.
So, and this would be then just 24, in fact. Or is it? Yeah, 24. And again, calculators out, it would be 2,98.
98.
Yeah, you're getting the same. Okay, cool. You can, I guess, give it also in cubic centimeters, but I don't know. I prefer cubic decimeters. Let's have a look at this will be 1 mark for the formula. I'm expecting, oh goodness gracious, I didn't even give the formula. I messed up with standard format, right? So formula substitution answer in science always. Right, so let me just make sure that I'm adding that. Oh no, wait, here I have the formula. That should be all right. And I've given formula here. That's all right. Okay, so formula, there will be a substitution for calculation of percentage. Substitution, molar ratio is going to get a mark, and 1 mark here. I believe that that will be the mark allocation. They might change this over to this substitution rather, instead of giving a mark allocation to the formula. Right, depending on how they're feeling. But that's a good one. 5.4, nice easy stoichiometry question. Let's go over to 5.5. How will the reaction rate increase? How will the reaction rate change if 15 grams of pure sample calcium carbonate reacts with the same hydrochloric acid solution? So 5.5. If it's pure calcium carbonate, there is not so much, not as many impurities. It's got a much greater chance to react with it, and so I'd say it increases. And it increases, I'm expecting they're asking us to explain it, of course. 5.6, explain using collision theory. In this case, it's not the fact that the concentration is higher, because it is a solid. Okay, just please note that. In this case, explaining why it would be better, it would not be the concentration, that the concentration is a matter of talking about, because it is a solid. We only talk about concentration in aqueous solutions. Right, so in this case, in solids, it's always going to be a matter of talking about surface area. Okay, so we're going to mention first, I'd say, greater surface area. Oops, so greater surface area. Why is it doing that today? Right, and then from this, we say that there will be using collision theory to explain an increase in reaction rate. And again, remember the reaction rate is change in concentration per unit time. And so again, if we miss out on mentioning per unit time, that's going to be important. But it's collision theory, so we need to mention more effective collisions per unit time. So don't watch out to not miss out on that. So greater surface area, and then lastly, or secondly, because it's only 2 marks, more effective collisions per unit time. Okay, because we are explaining a change in the reaction rate, and so we need to mention per unit time, and the effective collisions are what make it talking using collision theory. So greater surface area, more effective collisions per unit time. I'd say that whole section there is a very important part of explaining changes in reaction rate. You always end up using your final saying is always more effective collisions per unit time, or if something causes it to decrease, it's less effective collisions per unit time. So just take note of that. If they ask you to explain something with that affects the reaction rate using collision theory, this will be your final line. More / or less, depending on what the question is. Okay, so 1 and 2 marks, easy enough. Okay, let's move on. So reaction rate doesn't not necessarily need to be a challenging topic to deal with. There are a few small things that we need to mention that we need to remember. It is in explanation questions. Mention as many points as the mark has allocation, and also explaining reaction rate using collision theory. Almost standard. You will almost always get a question that asks you to explain reaction rate change using collision theory. And then this, getting to this final step here, more or less effective collisions per unit time, is important. Okay, on to the next question. Always going to be chemical equilibrium, also the type of question that you get the ICE tables in very, very often. Okay, so we're expecting an ICE table here, and you have shown that you are able to use ICE tables. I'll just, once we get there, I'm going to spot it. There we go. 8-mark question. That's going to be the ICE table. They are sometimes a bit daunting if you haven't started with them, or before you start with them, but knowing how to spot them from afar, being prepared for them, and knowing how to work on them is important. Okay, let's have a look here. 6.1 question. They start us off saying, consider the balanced equation below for a hypothetical reaction that takes place in a sealed 2 cubic decimeter container at 300 Kelvin. All right, so the container is sealed. That means that the volume is kept constant, as well as the temperature, I'm assuming, is also being kept constant. They've not mentioned that it's constant, but again here, oh no, wait, hold on. Later on, they say that it is increased to 350 Kelvin. All right, so that does change throughout. So we've got 2p in gas phase plus q2 in gas phase, making 2pq also in gas phase. Okay, so all three of them are gases. That might be important for us. Define the term chemical equilibrium. So chemical equilibrium, I've seen in your baseline test, you got it right. Most important part there is the rate of the forward reaction is equal to the rate of the reverse reaction. Okay, it is a chemical reaction where the forward reaction rate equals the rate of reverse reaction. Okay, so essentially you do not need technically this first part, chemical reaction, where the only thing that's important generally according to marking guidelines is forward reaction rate equals the reverse rate of reverse reaction. The forward reaction rate is equal to the reverse reaction rate. 6.2, the amount of each substance below, here we go, 6.2.1, the amount of each substance present in the equilibrium mixture at 300 Kelvin shown in the table below. Okay, and so the amount of mole at equilibrium of P is 0.8, Q2 is 0.8, and PQ is 3.2. Now the temperature of the container is increased to 350 Kelvin. When a new equilibrium is reached, it is found that 1.2 mole of P is present in the container. So 1.2 mole. So when the temperature is increased, the mole of the reactants increased. That's going to be important for us. Okay, because if the reverse reaction is favored when temperature increases, that means that the reverse reaction is what type of reaction, Emithla?
I think so. It's a exothermic reaction.
Let's have a think about it. An exothermic reaction, exo releases energy to the environment, right? So it gives off energy. And endothermic absorbs. Let's put like absorbs. Now, which one of these will enjoy more temperature, more energy? Is the exothermic going to enjoy more energy being added, or is the endothermic, what is going to be helping the reaction along? The one that uses that energy, or the one that is also just giving off? Okay. And here it is going to be important. The exothermic reaction, the endothermic reaction is favored by an increase in temperature. I think I might be right on that. But the endothermic reaction is favored by an increase in temperature because it wants that energy. It uses that energy. So when temperature is increased, the reverse reaction is favored. That means the reverse reaction is endothermic, but the forward reaction then will be exothermic. Okay, that's again just interpreting the question before we even start. So let's have a look. 6.2.1 is the heat of the reaction. That means enthalpy change, positive or negative? Ooh, now, okay, so now we need to remember what happens when enthalpy change is greater than 0 or when it is smaller than 0. What does this mean and what does this mean? Okay. And so if the enthalpy change goes from higher to lower of a reaction, that means that energy was lost. Enthalpy change started high and it went down. So the change in enthalpy was negative, right? This is a negative change in enthalpy, but this is an exothermic reaction. So this is exothermic, this is endothermic. Because now we get to the question, they're asking us, is the heat of the reaction positive or negative? We said the forward reaction is exothermic, and so it is going to be smaller than 0. It is negative. Right. Okay, so we have said a lot here. I have mentioned quite a few things here. I'm just going to take note here in green what we said. We said that the forward reaction is exothermic, the reverse reaction is endothermic. Okay, and we'll just erase all these notes here just to make space. Okay. This is a good thing, good practice to leave our notes on the back of the question paper of our answer booklet, just to make sure that they don't interfere with our answers here. Okay, 6.2.2, excuse me. Use Le Chatelier's principle to explain the answer to 6.2.1. Okay, and so Chatelier's principle, just a reminder, is that equilibrium will be reinstated by the reaction that opposes the change. Okay, the reaction that opposes the change will be favored. I'm just going to take a sip of water. So, excuse me. Now, using Le Chatelier's principle, again, there is a certain set method that we can answer this. Note this is a 3-mark question, so we will need to mention 3 things. We first mention fact. Increase in temperature favors endothermic reaction. We tell us, what do we know? What do we know are the facts? We say that an increase in temperature favors endothermic reaction. Okay, that's our first step. That's what we need to mention. That is fact. Now let's understand what's going on in the question. The reverse reaction is favored. Yeah. And so therefore, the forward reaction is exothermic or the reverse reaction is endothermic. You can go both ways. Okay. So I like saying the reverse reaction is endothermic because we are talking about the reverse reaction, but you can go both ways. So the reverse reaction is endothermic. I would maybe for completeness actually say then the forward reaction is exothermic, just to make sure. And forward is exothermic. But this is standard. Exothermic and endothermic, that is, if the forward reaction is endo, then the reverse reaction is exo, and vice versa. Okay, so that's important. But here are 3 points for 3 marks. Okay, I'm going to make some space here because here comes the big 8-mark question. I am expecting some ice table to be drawn here, and so let's prepare ourselves for that. Okay, so an ice table can be using concentration as well as mole. We can set up the ice table talking about concentration, but you can also set it up talking about mole. So let's have a look here. Now calculate the equilibrium constant at 350 Kelvin. All right, so let's have a look. We have an ice table and we're going to set it up. We've got some initial moles. I'm going to be working in moles because they do give all the values here already in moles. Okay. And so we've got our ice table. That means our initial mole and then our change in mole. And then our equilibrium mole. And then we can finally go to the equilibrium concentration. Right. So that's my ice table. Start drawing it. You don't technically need to do the ice table. It's not required from the department to draw an ice table, but it really is helpful. Let's just make sure we've got our products, our P, our Q2, and our PQ. Okay, so our P initially, before the change happened, was, let's just finish the table here. Our P was initially 0,8. Initially what, oh wait, hold on, this was at equilibrium. Oh, okay, so this was now, I think would be important for us to understand. It says here at equilibrium, but then a change took place and then a new equilibrium was established. So I can understand we might be inclined to say, oh, this 0,8 and 0,8 and 3.2 might be good for these positions. But what they're asking is for equilibrium constant at 350K. And so we need, that's after the changes happen. And so we can see this is our initial. So I would say that is 0,8, 0,8, and 3,2. Right, so if we see that as our initial. Yes, go for it.
Because it's 0,8 because there's a new established equilibrium. Because we were given before that, we were given initially that we have a equilibrium at 3K.
Say again, can you just repeat the question?
I was saying, how do you know if the equilibrium given initially to the initial mole, or to write it
in, so you
or to write it the relevant equilibrium?
Yeah, you want to know why is it here, why am I writing it here initially instead of here at equilibrium? Okay, so I think we need to just maybe step back and look at the question as a bigger picture. They're telling us that there was a container set up at 300 Kelvin, and this and this and this was found in that container, right? There was some reaction taking place. It's at equilibrium, and at that equilibrium we had 0,8, 0,8, and 3,2 mole respectively of each of those three. You with me?
Yes, I'm with you.
So there was a happy place. Everything was nice and stable. It was in equilibrium, but this was at 300 Kelvin. Then they decided, okay, let's make a change. What did they change?
Oh, now I see.
You see, so even though this was,
they stated that a new equilibrium was established.
yes, exactly. And so yes, this was also technically at equilibrium, but it was the old equilibrium. It was where we started, and then we made a change. This change came because of the temperature, right? So definitely it might just take some time. That's why, as I said, with all these questions, often just taking a second, making sure we understand what's being asked is actually probably more important than doing the question itself or jumping in beforehand. Okay, so, but good that you're asking. Love it. Absolutely love it. Okay, let's go. Because I also, when I started writing it in, I almost wrote it at equilibrium, and I needed to just double check. I needed to just make sure I'm doing the right thing, because it's easy to make mistakes like that. All right, so let's have a look. Now the change happened. I don't know what the P became, or do we? They do tell me that 1,2 mole of the P, of this P molecule was made. Okay, so they tell me at this new equilibrium, 1,2 mole was found. Right, and so we can find the change. We can know the change here. The change to go from 0,8 to 1,2 is 0,4. We're adding 0,4. I need to now just go have a look. What is this ratio? It's a 2 to 1 to 2 molar ratio. And so if 0,4 of P2 has been now created, that was the change, we will have half of this. And so that's going to be 0,2, because for every 2 of P, only 1 of Q is needed, or is created at least. Excuse me. It's a 2-to-2 ratio, and here again, it's going to be 0,4, but because the reverse reaction is favored, it's going to be subtracted, right? And so we end off with this, and we end off with 2,8 over here. We've got an equilibrium mole, and it's important now just to remember that this is a sealed 2 decimeter container, and even after temperature changes, it's still a 2 decimeter container. And so concentration is going to be mole over volume, right? So I would still say do the formula. Just do it once. I wouldn't say do it all 3 times. You can just show the formula the once, because if they are going to allocate a mark to it, they don't need to see it 3 times. So 1,2 over 2, that is 0,6 mole. Let me make some space. 0,6 mole per cubic decimeter. This is 1 divided by 2, which is 0,5 mole per cubic decimeter. This is 1,4. All right. Okay, so now we've got the concentrations at equilibrium. At our new equilibrium, we're looking at finding the equilibrium constant. And so that equilibrium constant, that is my Kc value. And a reminder that we set up this equilibrium constant not with solids or pure liquids, only with aqueous solutions and gases, but with the products, PQ, over the concentrations of the reactants. Okay, and so P and Q. We also need to take in, just and bear in mind, there's a ratio there. And so the ratio of PQ, that 2 will go there. The ratio of P, that 2 will go there. And setting up this formula, okay, please don't ever not set this up. I know sometimes it feels a bit silly, because it can become relatively easy to do it after a few practices, but don't not set up this formula. That always does get a mark. All right, and so 1,4 squared. We add brackets. Would you get out your calculator and maybe start doing the substitution already for us immediately? So we've got P,
Okay.
0,6 all squared and 0,5. And then I'll do it the same on my side, and we can see what we both get. Okay. So
So I'm getting 10,89.
10,89, just going to double check. Always good to double check. I'm also getting that. Okay, so good. 10,89. What are the units for the Kc value?
Hertz.
Say again.
I think it's Hertz, sir.
Is it? That was actually a bit of a trick question. There is no units. There are no units for Kc value. Okay, it's a unitless cell. It's a unitless value. Okay, so we never have to give any value there, and in fact there is no value because we are taking concentration dividing by concentration. It's a ratio at the end of the day. It tells us how whether the forward or reverse reaction is being heavily favored or not. Okay. So I expect we're then going to ask us now maybe something about that. Let's have a look. We've got some time still. Maybe we can finish off this question 6 today. Okay, so let's continue here. We've got 6.2.4. How will the equilibrium constant calculated in question, okay, there, that 10,89, be affected when the volume is either increased or decreased, or when the volume of the container is decreased at constant temperature? All right, so what do we think? How is equilibrium constant affected by change in volume? Is the equilibrium constant affected by change in volume?
No, sir. I think
It's not, eh?
It's not affected.
It's not. It's not at all. I think you're correct. I think you're correct. I think it just will remain the same. So there are only a very certain number of things that will affect the equilibrium constant, and volume is not one of them. Okay, so we need to just bear that in mind. The equilibrium constant generally is only ever affected by temperature changes. Okay.
Temperature. Yes,
Yeah. So, all right. See, I think we both got there at the end at the same time. It's definitely only temperature changes. Okay. All right. Okay, let's continue and let's finish off this question here. We've got 6.3. Let's go 6.3.1. Now they've got a question. Okay, now they're telling us more of Q2 is added to the reaction mixture at constant temperature. Okay, so it's remaining constant, whatever the temperature is. How will each of the following be affected? Choose from either increase, decrease, or remain the same. So if more Q2 is added, how will the yield of PQ? So if that means that the concentration, remember the volume is still remain the same, it's still the same container. And so concentration of one of the reactants, concentration of Q2 goes up. And so that means that Le Chatelier, remember Le Chatelier says that the reaction that is opposes the change will be favored. So if I'm increasing the concentration of Q2, the reaction that
I think that
decreases it,
the yield of Q will increase.
the yield will increase 100%. You're 100% correct, because the forward reaction is being favored. Le Chatelier's principle tells us if I increase this, and I'm referring now to the concentration of Q2, Le Chatelier's principle tells us the reaction will be favored that decreases it. And what is the reaction that uses it up? It is the forward reaction. Okay, and so that forward reaction will be, and so therefore, if the forward reaction is favored, more products will be made, and so the yield will increase. And again, when they tell us to only choose from increase, decreases, or remains the same, we have to choose exactly one of those three, and nothing more, nothing less. Not a single word may be changed in our answer compared to those three. And now they ask us, choose increases, decreases, or remain the same, but the number of moles of P, and using that same logic, we said the forward reaction will be favored. And so what about P? More of it will be used up, and so there will be less of it. And so for that reason, it will decrease for sure. As well, if I would be adding more of Q2. All right. I think we're going to stop there for the day. And then we can continue on next time. We're looking at a little bit more on the acids and bases. I think this is a good place to stop. All right.